Welcome to Partial Differential Equations, Part 10. During this lecture, we'll be looking at, continue looking at second-order equations. In particular, we'll be focusing on elliptic equations and methods for solving them. Up until this point, we've been finding the general solution of linear second-order equations. And what we'll be focusing from now on is looking at theorems that describe solutions or that are applicable to solutions, as well as how to find specific solutions given specific boundary conditions. It turns out that in elliptic equations, the boundary plays a very important role, not only in the solution and the nature thereof, but also in the method of solving. And we'll be looking at, to start, the Laplace equation and applying ideas from complex analysis to it, and do two examples. This lecture is in two parts, and so there will be an intermission in between the two in which you can review the material of the first part before going on to the second. Right, so just remind you, Laplace's equation in two dimensions, which is given over here, is one of the simplest elliptic equations we have. It has the normal form, it's equals to 0, so there's no other complications. And basically what we're going to be doing this lecture is looking at some of its properties by finding explicit solutions. And the method of finding solutions is actually very closely connected to complex analysis. So if you recall, we have our complex function f of z, where z is x plus iy, and we can express it in terms of its real and imaginary part. And there is a theorem that says it is analytic if both the real and imaginary part basically obey Laplace's equation. So there is a very close connection between complex analysis and finding solutions for PDEs. And in this case, the connection is exact. And we will therefore be using ideas from complex analysis to actually find explicit solutions to Laplace's equation. And this actually stands as a stepping stone to more general methods for finding solutions given a boundary and given an elliptic equation that we'll study in subsequent lectures. Okay, so just to remind you, because I'm assuming that you've had at least a basic complex analysis course, there's something called Cauchy's Theorem that has to do with analytic functions. And what it says is basically if f of z is analytic on a region R of the complex plane, and that region R has boundary G, okay, then the integral on the boundary, the closed curve around the boundary of f of z, dz is equals to 0. So just to remind you, f of z being analytic, you can basically say is equivalent to f having a power series expansion at each point of z in the domain R and having an inverse. So this is basically the sketch we have. Suppose you have a random yellow region R. If f is analytic on that whole region, if you were to take the integral along G, which is this blue curve along the boundary, and you would traverse it in the following manner. Remember, any line integral, the angle, the manner in which you traverse it is important. So in other words, you traverse it counterclockwise, basically obeying the right-hand rule. You have dz, and you go around this way. If you evaluate f on that integral, the whole integral, it is equals to 0. Okay, so that's Cauchy's theorem. There's an additional theorem, a Cauchy's integral theorem, that has to do with poles in a region, and what it says is the following. Suppose f of z is analytic on both the region R and the boundary, then for any complex number z in R, the following is true. You can write f of z inside the region as 1 over 2 pi I, the integral around on the boundary G of f of w, divided by w minus dz dw. In other words, it's an unusual result, but it's one of the foundations of complex analysis, is that the function inside can be evaluated at a specific point, can be evaluated by the integral of the function simply evaluated on the boundary over this pole, which is w minus z. Okay, so that's Cauchy's integral theorem. And if you are not familiar with these things, I encourage you to look at your third year complex analysis course, because these theorems will be featured there. Okay, so what we're going to do is we're going to use these two results to actually solve Laplace's equation, or more specifically to write down a solution to Laplace's equation on in 2 dimensions on regions with different kinds of boundaries. And it's a very cute result. I like it very much because it makes use of the full machinery we have from complex analysis to write down very elegant solutions. So the first place where we're going to apply this is to find a solution for Laplace's equation on a disk. In other words, on the region x squared plus y squared is less than a squared, if we are given the value u on the boundary, so x squared plus y. So if we know that what u is on the circle around the disk, and we know that u obeys the Laplace's equation, we now want to write down a solution for u throughout the disk. And we're basically going to use Cauchy's integral theorem and Cauchy's theorem to be able to do this. Okay, so let's just set up the problem. We're going to use our complex variable z. The complex conjugate is z bar, which is just x minus iy. The norm of z is basically x squared plus y squared, and we're denoting it that way. And we can also express z in terms of polar coordinates, which we will actually use to write down the solution succinctly. So we can set z is equals to r times e to the I phi, and once again, the norm is simply r, which is assumed to be greater than 0. Okay, and the approach now is to use this Cauchy's integral theorem to actually get an explicit expression for z if we're given z on the boundary. So we now want to find Laplace's equation on the disk, everywhere inside the disk. We're given Laplace's equation on the circle of the disk, and I've already given you the hint that we're going to use the Cauchy's theorems to be able to do that. So now the first thing I want to note is sort of some just features of the complex number. So suppose we pick a z over there, we say z is x plus iy. Note that the conjugate of z also lies in the disk, so z bar is this, x minus iy. But a squared over z bar lies outside of the disk. Okay, so let's just see why that is. So we say if z is less than a, in other words, it lies within the disk or inside the circle, then we're going to have that a squared over z bar lies outside the disk, and we're going to show that by simply showing that this norm is greater than a. So the way we do that is we have the norm of the real is just a real, so we have a squared over the norm of z bar, which is equals to a squared over the norm of z, which is greater than a. Okay, because z by definition lies inside the disk, so z is less than a. Okay, so we now have another complex number that lies outside the disk, and the reason for constructing this number will become apparent in a moment. Just for the rest of the discussion, it's useful to define z in terms of polar coordinates, and there we've written it out. And also just to simply to note that a squared over z bar, in other words, this point over here, you can express as a squared over r times e to the minus I phi, but if you put that above the line, it is e to the I phi. Okay, and therefore you can also write it as a squared over r squared times z, where I've multiplied e to the I phi with r, and there's another r above and below the line, and basically that's where we get. Okay, so now the discussion goes, if z is in R, okay, then this function is analytic in R if f of w is R. Okay, so let's just look at this. this W, since a squared over z bar lies outside of z, a squared over z bar lies outside the disk, and W lies inside the disk, this thing is never zero, and therefore this function is analytic because f of W is analytic. Okay. And because it is analytic, you can use the first Cauchy's theorem to say that the integral of the line integral of this function along the boundary of the disk is equals to 0. Okay. And what you have as a result is you can apply this thing twice, right? You can apply the first part, you can have Cauchy's integral theorem, that's the one in the red box, is simply given here, which is basically that f of z is e to the 2 pi I, the integral of g f of w over w minus z, where this pole actually does appear in the disk. Okay, so that's Cauchy's integral theorem. The second part, we've shown over down here that it's 0, so we're free to add it. But the reason we add it is going to become apparent when you notice that that thing ensures that it makes it easy to put the boundary conditions on. Okay, so we've basically written, what we've written down here is Cauchy's integral theorem, the thing in the red box, plus a factor that is actually 0. And we know that f of z is equals to that. And what we'll now do is we'll proceed to simplify this expression in brackets and see what the implications are, and it'll become apparent why we had to add, the second bit to the integral. Okay, so let's evaluate that thing and see what we get. And to evaluate it, we're going to set W to be the complex number on the boundary. In other words, A is fixed to the boundary times e to the I phi, which is the angle as we traverse the boundary. And therefore dW is equals to IA e to the I phi d phi. So I'm going a little bit slowly, and I'm assuming you are not totally in practice with complex integrals. So be careful when you go from this integral around the boundary of the complex plane to actually your real variables, and look at the way I do it. Okay, so what we want to do now, you can always factor out f of W and put it here. And then you're left with 1 over W minus Z. W is always stuck on the boundary, and you can express it in polar coordinates that way. Z is any function in the actual disk, and you can express it using those polar coordinates. Right, minus 1 over W A squared over Z bar. Okay, and we can put it over, we can basically firstly put all the complex numbers in the numerator, so you multiply above and below by the complex conjugate to get W bar minus Z bar plus the norm of W minus Z squared, minus, and you do the same thing over here. You multiply below and above by the complex conjugate, so the complex conjugate of this is W bar minus A squared over Z bar, over Z, because it's a complex conjugate of that, which is then simply O equals to A squared over R times e to the minus I theta. Okay, and below here we have the norm of the complex conjugate. Sorry, the norm of this thing below the line. Okay, so now let's evaluate the things in the denominator, because the natural thing is to try and put the two things in the two things over a common denominator. So the norm of W minus Z, in other words, that comes from this, is simply W squared, is simply W minus Z times W bar minus Z bar. And if you multiply that up, you get W times W bar plus Z times Z bar minus W bar Z minus Z bar W. Okay, so this is the first norm, and that simply equals to WW bar is simply A squared, ZZ bar is simply r squared, and w bar z minus z bar w is simply you combine these two expressions to get that. Okay, so that's just manipulation of complex numbers, and you have basically a cos of theta minus phi coming through. If this is unclear, I encourage you at this point to actually pause the lecture and just make sure that you can write it out for yourself and do the complex manipulations that gives you this. Okay, the next part is to look at the grey part and to try, or the grey denominator, and to try and evaluate that. And you do the same thing. To work out the norm, it's just w minus a squared over z bar times basically w bar minus a squared over z, and you multiply it through, and what you get is w times w bar plus a to the fourth zz bar, which is just r squared, minus a squared over basically z bar, which is r e to the I theta, times w bar minus a squared over w times the complex conjugate of this thing, which is just a squared over z, which is e to the minus I theta times r. And so these first two terms, w bar is a squared, you have a to the fourth over r, and then you substitute r equals a times e to the I phi in there, or you substitute w equals a times e to the I phi over there, and w bar equals a times e to the minus I phi over there. And you see once again that cos factor is coming in, because you have e to the I theta minus phi, and here you have e to the minus I theta plus phi. And okay, so there we go. You factor out the term in front, which is an a squared times a from w over r multiplied by these two things. Okay, and there you have that you can write down an expression for the norm, this grey norm that appears in the denominator, and you factored it out, and you can notice that it is exactly the expression that appeared over here in brown. So what you have is that the one norm is merely a factor of the other one, and that w minus a squared over z squared is simply equals to a squared over r squared times this thing in brackets, which is simply w minus z bar squared. So we now are in a position to substitute basically this grey expression for this one and simplify what we were trying to calculate to enter the integral up at the top. Okay, and here we have it. So we now have that 1 over w minus z minus 1 over w minus a squared over z bar. We put it over a common denominator, and there we go. So we have the first term, w bar minus z bar, plus basically r squared over a squared times these other terms. Okay, so we've basically multiplied this thing by r squared over a squared, because we replaced the grey thing with this denominator. So there we have a common denominator. What we can do next is substitute in or simplify the problem, because we have a z bar minus z bar here and a z over there, and we get w times 1 minus r squared over a squared over this norm. Okay, so we've now simplified what this complicated sum of two complex fractions is that appears in this integral, and we've in fact got an expression for f of z, where f is a complex number inside the domain of the circle, basically inside the disk, which is equals to this integral of something on the boundary. And we're just going to write this thing out now using this expression for the complex manipulations, and it's going to become apparent why we actually made this choice. Okay, so here we have f of z. It's exactly the expression that was on the top of the second column of the last slide. It's 1 over 2 pi I times the integral from 0 to 2 pi, and we're integrating over the boundary, so the angle goes d phi. F of w, which is the complex number on the boundary, times this factor that we calculated on the previous slide, times, remember it was, we're replacing the line integral on the complex plane with a now and actually a real integral, so our dz becomes ia e to the I phi d phi. Okay, so this is an important point. This is only true because we're actually working on the circle. You'll see in subsequent examples that taking that transition from the complex integral to the real integral must be done with care. Okay. The great thing is over here is that I then cancels with this thing, and we can simplify it as follows. Okay, so here we have it again. The expression for the integral, we simply have this ia e to the I phi that comes from the dz times w bar, which is just a e to the I phi, times this factor, which is real, times 1 minus r squared a squared, plus over this denominator, which we actually worked out the difference between w and z in the previous slide. And we can simplify it, so we cancel out the i's to get 1 over 2 pi. We have a squared multiplying this thing through, so we have a squared times 1 minus r squared. So that's where that term comes from, and then below we still have this denominator. Okay, so this is now very nice because we have this complex function inside the domain, which is equals to what appears to be a real integral. In other words, this term in brackets is real. The integral, it's the integral from 0 to 2 pi, so along integral on the angle of the circle, 1 over 2 pi. The only thing that could possibly be complex now is f of w. Okay, and so let's just expand it a little bit. So the first thing to observe is that on the boundary, basically f of w is equals to a times e to the I phi. So all I've done is replace w with a with its complex version, or with its a polar version, and I can equivalently write that as two functions of phi, right? This is simply the value of f evaluated on the boundary. So we have a real part of this complex function, and we have an imaginary part of this complex function on the boundary. And you can also write f of z equals to f of r times e to the I theta, so we're basically replacing this thing now, as a complex function in r and theta, so u of r and theta plus I of v of r and theta. And if you do that, and you consider only the real part of this function, you get the following expression, right? Because the only complex value, or the only complex parts of this integral is in f, and f of z is potentially a complex function, we can simply take the real part directly, and we have that u of r and theta is equals to 1 over 2 pi times this integral from 0 to 2 pi f1 of phi times this expression over here in brackets times d phi. Okay, so in practice, we actually have an expression of u, given what u is on the boundary, multiplied by all these other things where r and theta appear. The integral is over phi, and it's a closed form expression. Okay, and the bonus that comes out of using Cauchy's theorem is we know that because we assumed f to be analytic, the Laplacian of u vanishes on the region R, okay, of which the boundary is now, in this particular case, a circle. And we know that f1 of phi is basically the real part of f on R itself. Okay, so we know that f1 is the initial value that we are given for u. Okay, so f1 of phi is simply u a of phi, and so we've actually solved the problem. Okay, so f1 is the value of u on the boundary. We know that u satisfies this Laplace equation on that region R, and so we actually have found, using this expression, a valid solution for Laplace's equation that also satisfies this boundary condition. Okay, in subsequent work we're going to show that once we've got one solution, it's unique. But for now, we can satisfy ourselves just that by using this complex, the Cauchy's theorems of the complex plane, we've actually got a solution we can write down for anything that is given on the boundary. And this is reasonably powerful because in some sense we've solved the equation and we've reduced this very basically a second order partial differential equation to an integral, which you can always evaluate. And even if you change what value of u is on the boundary, you still have to evaluate the same integral. So there's a lot of the solution you can actually learn from this expression. Okay, so I think this is going to conclude part 1. I will start part 2 shortly, or I'll actually put it in another video, but I strongly encourage you to actually go through the argument and make sure you understand it before completing part 2, because it's going to be just another example of the same technique.